chapter to get into, which is solutions to systems of differential equations. We're going to do that by means of matrix algebra. So that is by solving the eigenvalue and eigenvector equation. But well, before getting into that, we will do a basic review of some of the elementary matrix operations that you should know from college algebra. And some of you, maybe who are taking linear algebra or have taken it before, uh, you're familiar with some. Okay, what are we going to do? Review the elementary operations, of course. Do some examples to briefly review, and compute the determinant of a square matrix, which is a big thing. Okay, we need it for the whole chapter, pretty much. Okay, number one, what's a matrix? A matrix is defined as a rectangular array of numbers, and they're denoted this way. So you have like brackets or parentheses with a lot of numbers inside this array. So guys, that means we have two different ways to denote matrices. We're using like the brackets or the big brackets or the big parentheses. All right. Well, the way we describe a matrix is by its number of rows and columns in that order. For instance, when we when we look at matrices, so we see a matrix and we should be able to determine its size. For examples, right here, what do we have? Matrix A. How many rows? Those are the horizontal arrays. In this case, we have a total of 3 rows. Okay, by 4 columns in this case, all right? It's never the reverse. Rows first and then columns. Number two, or rather letter B. How many rows and how many columns is this one? What is that? It's 3 by 2? No, yeah, 3 by 2. 3 rows, 2 columns. What about matrix C? How many rows do we have over here? 5, and how many columns? 9, so 5 by 9, right? Okay. What about the next one, letter D? How many rows? Just 1 row. How many columns? It's columns 8. So 1 by 8. In fact, well, what about letter E? How many rows and how many columns? So how many columns? 1. How many rows? I mean, how many rows first? 1, 2, 3, 4, 5 by 1. Well, actually, the last two are usually called row vectors and column vectors, respectively, because we have only 1 row or only 1 column. Actually, matrices can also be thought of arrays of vectors. For instance, here, matrix C actually has uh, 9 column vectors and 5 row vectors, depending on how we want to see this. All right. Okay. So what are the operations we do with these vectors? So number one, if we consider two matrices A and B with entries 1 and 1, 2, the subscripts of the entries here tells us the element A, which is in the row 1 and column 1, for instance. This entry right here is in still the first row, row 1, and column 2. Again, the order of how do we describe a matrix actually matters. First, the number of rows or the location in the row, and then the columns. Okay, so what do we do? So we define the sum or difference of two matrices as follows. Sum or difference, all we do is simply combine the terms, the corresponding terms. So that'll be this addition or subtraction, as another example, 1, 2, B1, 2, A1, 2, B1, 2, combine them together this way. Now, there is a third operation. If we consider a scalar C, some number can be any real number. All we do for scalar multiplication, multiply all of the entries of the matrix by that same number. Notice how in this case we have all the entries multiplied by the constant c. Now we have a little problem. Well, good news and bad news. Matrix addition and also subtraction is commutative and associative. However, the sum or difference of two matrices of different sizes is undefined. All right. So that means we can only add, say, a 2 by 2 matrix with another 2 by 2 matrix, 5 by 3 matrix with another 5 by 3 matrix. We cannot add together a 3 by 4 matrix with a 1 by 2. No, we can do that. No, the dimensions, rather, the sizes must be the same for all the matrices. Okay, a special matrix, just like every number system, guys, every number system, um, there has to be a unit, like the real number system, the unit is a number one, or the zero is a number zero. Well, we have the zero matrix, which is the matrix having all zeros in its entries, and we have what we call the identity matrix. Uh, this is the equivalent to actually uh, have the number one. How does that look like? Well, it has ones along the main diagonal and zeros everywhere else, to denote some of them. Okay, I sub 2 denotes the identity matrix, the 2 by 2 identity matrix. I sub 3 denotes the 3 by 3 identity matrix. I sub 4 denotes the 4 by 4 identity matrix. Of course, we can extend this to size n, right? For an n by n. We're gonna do a few exercises about this one. Okay. What else are we going to do here? Oh, very important. The multiplication of matrices. And I don't mean the multiplication of a matrix by multiple scalar like we did, like I showed before. No. Here, two matrices can be multiplied. Well, when we arrange them together, A times B. So suppose we have a matrix that has m rows and r columns. In order for these two matrices to be multiplied, the number of rows of the second matrix to multiply must be the same as the number of columns in the first matrix. That is, so if we have an m by r times an r by n, for instance, these two must be the same. Okay, these two must be the same. If you have different numbers, that is, the number of columns in the first matrix is it different than the number of rows in the second matrix, then we can't move the multiplication is undefined. Now, the result of the new matrix we're going to obtain will be a matrix that is m by n. That is m by n. All right, you'll see about it. Okay. Now, matrix multiplication maintains the associative and distributive property. However, in general, is not commutative. For some cases, maybe, but for many cases, in general, it's not commutative. All right. Okay, so how about we see this in action with a couple of examples? Well, so let's see. Let's consider these three matrices here. Matrix A, which is let's see. Let's state the sizes of the matrices. This is 2 by 3, another 2 by 3, 2 rows, 3 columns, 2 rows, 3 columns, and how about this one? 3 by 3, 3 rows, 3 columns. In fact, that's what we call a square matrix. All right, we call that a square matrix. Okay, so well, let's perform the following operations. Well, they're asking us to evaluate 3a minus 2b, right? 3a minus 2b. Well, even without the multiple constants 3 and -2, first we need to determine whether a and b have the same sizes, so we can add them together. And in fact, we have a 2 by 3 with another 2 by 3, regardless of their multiple constant. Well, we can add them together. So let's set it up. And actually, I'm gonna go back and forth between the notations for these matrices, even though we're given matrices as in bracket notation. I'm just gonna change this to parentheses. So 0, 3, negative 5, 1, 2, 6, minus 2 times 4, 1, 0, negative 2, 3, negative 2. So just like in pre-algebra, PEMDAS. We do the multiplication first and then the addition. So let's multiply all the entries of the first matrix by 3. That's going to give us the following. So 0 times 3, that's 0. 3 times 3 equals to 9. Negative 5 times 3, that's a negative 15. And 3 times 1 is 3. 3 times 2 is 6. 6 times 3 is 18. And then I'm going to keep the minus here. Okay, I'm going to keep the minus. The alternative is to multiply everything by negative 2 and then keep an addition. But I rather keep the negative and then multiply all the entries of the second matrix by the number 2. So 2 times 4, which is 8. 2 times 1, which is 2. 2 times 0, which is 0. 2 times negative 2, which is negative 4. 2 times 3, which is 6. 2 times negative 2, that equals negative 4, all right? And finally, we will combine the two matrices together entry by entry. Like in this case, element 1, 1 with 1, 1, 1, 2 with 1, 2, 1, 3 with 1, 3. And then for the second row, 3, 1 with 3, 1, 3, 2 with 3, 2, and 3, 3 with 3, 3, right? I mean, 2, 3 with 2, 3, not 3 here. Okay. So let's simply combine these two together. That equals, open, 0 minus 8, that's negative 8. 9 minus 2 is that 7. Negative 15 minus 0, that's still negative 15. 3 minus negative 4, that's 3 plus 4, right? That's positive 7. 6 minus 6, that equals to 0. And lastly, 18 minus negative 4, that's 18 plus 4, which is 22. Okay, final answer. Okay. All right. That was letter A. What about letter B? A times C. So what do we have in this order? Again, the order of the product between two matrices actually matters. So A times C. We're gonna multiply. What is that? 0, 3, negative 5, 1, 2, 6, and we're gonna multiply that with C, which is 4, 1, 2, 6, 2, negative 1, negative 2, 3, 5. All right. Okay, guys. So it's not just multiplying numbers and numbers. So it's quite a process there's a process we have to do right here. Number one, can we even multiply these two matrices together? Okay. So number one, let's analyze their sizes. On the one hand, matrix A is a 2 by 3 and a 3 by 3 for matrix C. Well, do the numbers in the middle match? In this case, they do. So that means we can do the multiplication. So the number of columns of the first matrix must match the number of rows of the second matrix from left to right. If it's not the case, then the multiplication is undefined. Okay. So how do we go about this one? Well, remember the dot product from calculus 3? So we're going to do something similar, except that we're going to do a bunch of dot products here. For instance, check what we're going to do. So number one, oh, what would the size of the matrix be, of the resultant matrix be? It's going to be a 2 by 3 matrix, right? So that means we need to make space for a 2 by 3 that is one row with 3 entries and a second row with 3 entries as well, or 3 columns with 2 entries each, depending on how you want to see it. Okay, guys, you've seen this before, whether in college algebra or in linear algebra or even in intermediate algebra in high school. You may have done this, maybe not. But I mean, let me show you how we're going to do. So in this case, let me highlight, okay, this blue. I'm going to highlight the first row of the first matrix. and the first column in the second matrix, okay? So what's the element in common? What element do they share? They share the element, the A11 element, all right? That's where they intersect. So what do? Multiply 0 times 4 plus 3 times 6 plus negative 5 times negative 2, okay? You can do this in your head, actually. So 0 times 4 equals 0. 3 times 6, which is 18, and then negative 5 times 2. Actually, let me highlight each pair of numbers and multiplying. So, again, 0 times 4, which is 0. 3 times 6, which is 18. And negative 5 times 2, that's going to be positive 10 plus 18. Is that 28? Okay, that's 28. Okay, whoops. Now, what about the same first row? Okay, I'm going to go with the first row, but this time, and with this time with the second column of the second matrix. I'm going to want to multiply 0 times 1, which is 0, plus 3 times 2, which is 6, plus negative 5 times 3, which is negative 15. So negative 15 plus 6, what is that equal to? Is that negative 9? And, okay, what's next? The same first row on the first matrix, but now with the third column of the second matrix. So what do? 0 times 2, which is 0. 3 times negative 1, that's negative 3. And then negative 5 times positive 5, that is, so negative 3 minus 25, is that negative 28? Okay, negative 28, right? Okay, now we're done with the three columns on the second matrix. Now let's repeat the process. That'll be the second row, okay, of the first matrix with the first column in the second matrix. So 1 times 4, which is 4, plus 2 times 6, which is 12, that's 16, right? Plus 6 times negative 2, which is negative 12, that actually adds up to 4, right? Let me do second row with second column. 1 times 1, which is 1. 2 times 2, which is 4. 1 plus 4 equals to 5 so far. Plus 6 times 3, which is 18. So 5 plus 18, is that equal to 23? And lastly, what do we have? Um, lastly, with the last column, okay? So 1 times 2, which is 2. 2 times negative 1, actually the 2's cancel out. 6 times 5 equals to 30. And that is the resultant matrix, the result of multiplying these two matrices. All right? Essentially, we did 1, 2, 3, 6 dot products, right? That's essentially what we did. A total of 6 dot products. Okay, because again, these rows or columns represent matrices. Okay. All right. What about letter C? They're asking us to multiply 4 times C and subtract 6 times the identity of order 3. That is the 3 by 3 identity matrix. Okay, so for the 3 by 3 matrix, which is C, let me do 4 times 4, 1, 2, 6, 2, negative 1, negative 2, 3, 5, minus 6 times the identity matrix of order 3, or the 3 by 3 identity matrix. Okay? Again, first things first, multiplication, and then subtract the matrices. All right. So multiply all the elements of the first matrix by 4. Okay, so that is 4 times 4, that's 16. 4 times 1 equals 4. 4 times 2 equals to 8. 4 times 6 is 24. 4 times 2 equals to 8. 4 times negative 1 is negative 4. 4 times negative 2 is negative 8. 4 times 3 equals to 12. 4 times 5 equals to 20. We're going to subtract Well, the only entries that get affected by the multiplication by six are the ones in the main diagonal because everything else multiplied by zero, it's still zero. So six, 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 zeros everywhere else. All right. Now, okay, I'm not going to add all the or subtract six to all the entries. I mean, the some of the entries are going to remain the same because we're going to subtract zero to some of them. The only element that get affected by this difference are the ones along the main diagonal. So 16 minus 6, is that equal to 10? 8 minus 6, is that equal to 2? 20 minus 6, is that equal to 16? The other six entries just remain the same: 24, -8, and 12. 4, 8, and -4. Final answer. Final answer. Right? Yes. Should be which one? So 20 minus 6 should be 14, right? Yeah, 14. Thank you. Thank you. Yeah. All right. Good catch. All right, what about letter D? They're asking us to multiply C times B. That is 16, 4, 8, 20. Oh, wait. No. 4, 1, 2, 6, 2, -1, -2, 3, 5. And multiply that by what's matrix B? Isn't that 4, 1, 0, and -2, 3, -2? Okay, can we even multiply these two matrices? Why not? Why can't we multiply these two? The dimensions for, okay, what are the size? What's the size of the first matrix? 3 by 3. What about the second matrix? 2 by 3. So what's the condition so that these two matrices can be multiplied? Exactly the number of columns in the first matrix must match the number of rows because guys, what happens if you try to do the same process? Oh, okay, 4, 1, 2, 4, -2. So you would have to multiply 4 times 4, okay, whatever that is, plus 1 times -2, whatever that is. But what about these two here? There's no row of numbers here to keep multiplying that last entry. So that means undefined. Okay, undefined. Last but not least, A plus C. What about A plus C? So A, which is 1, I mean, no, 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 0, 3, -5, 1, 2, 6, plus, again, 4, 1, 2, 6, 2, -1, -2, 3, 5. Can we add those two matrices together? Why not? They're not the same size in this case, right? They're not the same size. So also undefined. Not the same size. Okay, not the same size. All right. Let's see. Oh, let's talk about the determinant. Okay. So, I mean, you may have done a lot of determinants already when you were solving systems of equations using Cramer's rule. Oh, in fact, we did a few determinants in variation of parameters, right? Also, where did we do determinants? The cross product of a vector also needs the calculation of a determinant. So you guys know a little bit about it, right? But I mean, what is it? You can think of the determinant as a function whose input is a square matrix. By the way, the determinant is only valid for a square matrix. We can't take the determinant of a matrix where the number of rows is different to the number of columns. So, and the output, it's a real or potentially a complex number. All right. So that's why our result would be UG. For a two matrix, for a 2 by 2 matrix, what do? We multiply the elements along the main diagonal, that is the diagonal that in this arrow took us from left to right, and we subtract the product of the elements along the secondary diagonal, AD minus BC. All right. Number number two, for a 3 by 3 matrix, guys. Okay, so I have to show you this formula right here, this what we call expansion by cofactor. But I'm going to show you a different, a quicker way to evaluate a 3 by 3 matrix, because for what we're going to do in solving systems of equations and getting the eigenvalues and eigenvectors, these calculations or the calculations of these determinants could be tedious. So, well, okay, number one, where is that formula coming from? So here you need to decide along which row or which column do you want to expand this. That's something you will get more, you'll get to see more in detail in linear algebra. I don't think this is something you get to see in college algebra, but anyway. So here, so if you observe these coefficients here, A1, A2, A3, it seems like, well, let me actually change colors to have a better match with colors here. Okay, let me do some purple here. Okay, A1, A2, and A3. Okay, so those three elements I highlighted actually are the elements of the first column of the 3 by 3 matrix, right? So that means this expansion was done along the first column. So how did they do this? Well, A1, what does the A1 represent? So number one, it represents the intersection between the first column and also the first row. Okay, so do you see the intersection of, well, in the highlighting is the element 1, 1? Okay. Now, do you see these elements B2, C2, B3, C3 that were left? Okay. These are in the smaller matrix. That's called the minor. Okay. So the first number right here, the first coefficient, A sub 1, it's the cofactor. This smaller matrix is called a minor. All right. A sub 2. That's the intersection between, again, the first column and the second row. Okay. Now, do you see all these elements I didn't highlight? B1, C1, B3, C3. They're here. B1, C1, B3, C3. So A sub 2 is the cofactor. B1, C1, B3, C3. It's the cofactor. Let me highlight the third row. And the element in common here is A sub 3. Do you see the elements that were not highlighted? B1 C1, B2 C2. Those elements comprise the minor of expanding this with cofactor equals to A sub 3. But guys, if you prefer, you can expand along the first row if you want. You can expand the other column. There's no limit. Usually you would expand along a row or a column that has most zeros, because multiplying by zero reduces a lot of the work. All right. Now you might wonder, because the first cofactor is positive, the second one is negative, and then the third one is positive. Where is that coming from? Well, you can always think of this matrix as an array of signs, like a checkboard, starting with positives. Okay, so oh wait. So let me do positive, negative, positive, negative, positive, negative, positive, negative, positive. All right. So this A1 is positive, this A sub 2 is negative, and this A sub 3 is positive because of the arrangement in the checkboard of signs in the matrix. All right. Okay. But guys, this expansion by cofactors in some cases may be a little tedious. I'm going to show you a different way to evaluate another rule, a quicker rule to evaluate this one. Now, for matrices that are 4 by 4, 5 by 5, well, there's no rules like for 2 by 2 and 3 by 3. In that case, you would need to reduce the big matrix into smaller matrix using elementary row operations, guys. Okay, so and then but of course we're not going to go with matrices that big. We're just going to do 2 by 2 and 3 by 3. Okay. Okay, let's evaluate this determinant here. So evaluating, that is 4 times 1, which is 4 times 1, minus negative 3 times 2, which is equal to 4 plus 6, which equals to 10. So that's the value of the determinant, 10. Okay. Okay, guys. The what about the 3 by 3 case? So I don't want to expand along and do this process and evaluate three 2 by 2 matrices. Instead, I'm going to show you a rule that it's called Sarus rule. Not too many linear algebra textbooks cover it, but if you Google it up, it's actually a rule. It's regarded as a shortcut, but it's actually a rule. Okay, so how does that work? So we need to repeat the first two columns, 2, 3, and 4, negative 3, 7, and 0, and then let's compute the product along the main diagonals. That's going to give us the following result. Okay, let me actually go with the colors. So that is 2 times 7 times 5. Is that equal to 70? Negative 3 times negative 2 times 4. Is that 24? And then 1 times 3 times 0, it's plus 0. Okay? Equals, and then we're going to subtract another group, multiply the elements along the secondary diagonals, right? The arrows coming backwards in a way. So that is negative 3 times 5. Is that 9 times 5? Is that 45? Negative 45. And then 2 times negative 2 times 0, that's actually plus 0. And 4 times 7, that's 28 times 1, that's 28. Okay? Simplify each group first. 70 plus 24, is that equal to 94? And negative 45 plus 28, that is minus, what is that, negative 17? And combine these together, 111, right? So, all right. Now, another quick, not shortcut, but I mean, if you happen to see one of these special matrices that they are called triangular matrices, uh, those are that's actually the best case scenario because, let's define what a triangular matrix is. So, a triangular matrix, it's actually a square matrix with all entries on one side of the main diagonal being zero. So, there are two types. The upper triangular, which has elements along the main diagonal and entries above, but zeros below, and lower triangular with all zeros above the main diagonal and non-zero entries below the main diagonal. Well, there could be a zero, or could be all zeros, right? That's actually a thing. All right. So in this case, the matrices I'm showing you here represent 3 by 3 triangular matrices, but actually this can be extended to n by n case, 5 by 5, 97 by 97 triangular matrices, and well, they're still the same. They're still the same type of matrices. Now, the good thing about this one is to compute the determinant of a triangular matrix, just multiply the elements along the main diagonal. If you happen to see one of these, that's all you have to do. You don't have to do expansion by cofactors and minors or the Sarus rule. So that's all you do. Okay. So evaluate the determinant of A equals to negative 300, 580, 13, negative 6, 2. Okay. So number one, the determinant of A would be, and by the way, guys, for the determinant, be sure to use the proper notation. We don't use brackets or parentheses for determinants. Just go with bars like absolute value bars, negative 3, 5, 13, 0, 8, negative 6, 0, 0, 2. So in this case, because this matrix happens to be triangular, all we do is multiply the elements along the main diagonal to find its determinant. All right. So That means -3 times 8 times 2, is that equal to -48? So that's what it is, right? -48. All right. It seems like this is the end, right, of the section. So this was a basic review of elementary matrix operations and, of course, a little bit of linear algebra, even though, well, we're going to use quite a bit of this, okay, in the next following sections.